quick update on progress with my 6502 breadboard computer. This is a Ben Eater style breadboard computer. If you haven't seen his videos and tutorials, do check them out if you're interested in this kind of thing. They're excellent. I want to build a self-contained computer that I can program in machine code on a hex keypad using a simple display for output, a bit like a Kim 1 or an Acorn System 1, one of those sort of mid-1970s single board computers. And so to that end, I've got a 4x4 matrix keypad. These are very cheap membrane keypads, and I've connected it to the versatile interface adapter via an encoder chip, which is on this breadboard. You can't quite see it, it's in the shadow. And I've wired up to the output of that encoder chip 5 LEDs. The red one you'll see is the data available light, and that is triggered whenever you push any key. And that is connected to one of the interrupts on the VIA. So that sends an interrupt signal to the processor up here and says, hey, I've pushed a button. I want you to do something. In this case, read which button I've pressed. And you'll notice on the display here, when I press different keys, the relevant character appears on the LCD display. So that's kind of a proof of concept. I've borrowed the hash key as E and the star key as F. So that means I can enter hexadecimal opcodes on here. And hopefully eventually I'll be able to get them in memory. I'll be able to run my program. So that's all well and good, but I can't actually run any programs. I need some more buttons to sort of step through memory locations, stop the program running, start it, all that kind of thing. So I need some more keys, and I've run out, and I've only got one pin left on the versatile interface adapter because I've used most of them for the LCD display. A lot of the pins here are driving the LCD display rather inefficiently, and I've used 4 of them just to encode the data of each key that I press, because you'll see every time I push a key, a different pattern of green LEDs appears. They're all connected to port A on the versatile interface adapter. And basically, it's a binary number. It's a 4-digit binary number. Each different digit represents a different character on the keypad, and I'm reading that in my program to decide which letter it is or which number I've pressed on the keypad. So I've got a bit of a problem. I've only got one pin free. I reckon I need at least 4 more buttons to make a proper monitor program where you can enter a program, edit it and run it. So I've got my one spare input. I have wired it up via a pull down resistor here to a switch, a push button. So now if I press, hold down the shift key and I press D, it will step forward through my program, and you'll see it's stepping through different memory locations. It's showing you the contents of that memory location in hexadecimal, and also an ASCII representation of what's in that location as well. And I can step backwards as well. If I hold down shift and press C, that goes backwards through the program. So that's a good start. I'm going to need to wire up some more buttons to do go and stop. And I'm going to need to make it so that when I'm pressing these keys, it's actually changing the contents of the memory locations. That's my next step. But it's a really, really good start on the path to making a monitor program. The other interesting thing I found about wiring up the shift key was the need for a pull down resistor. I thought, well, I'm just going to send 5 volts to my spare pin when I push it, so I'll know when shift has been pressed. How hard is that? So I literally just put that switch between 5 volts and the input. I soon discovered that didn't really work, and it was a really interesting way of finding out that you can't leave these kind of digital inputs on things like versatile interface adapter chips. You can't leave them floating. It was fine. It was new when shift was pressed, but when I let go, its state was completely unpredictable. It could stay in the high state, so you have to pull it down. So that's why we've got it tied also to ground via a 1k resistor. I think I put in there. I can't actually remember the value now, but anyway, I've got a resistor tying it to ground so that when the switch is not pushed, it is definitely being grounded, and when I've pushed the switch down, it is going high. So it was a good lesson for me, a very practical representation about why you actually need pull up or pull down resistors in this kind of logic work.
Please hang up and try again.